Now, we've been working on Lewis dot structures, and you may have already noticed some patterns starting to emerge, but I want to have a short tutorial and to call your attention to these bonding patterns of, in particular, second row elements. So I have to admit that we organic chemists are really not very adventurous, and we don't often venture too far beyond the second row. Yes, we get a little bit into the third row elements, not so much though. Pretty much we are interested in, as I said, second row elements. So let's talk a little bit about the bonding patterns. Now, if we look at the left side of the periodic table, these first two families, we have the alkali metals and alkali earth metals. Now remember that they are not very electronegative, and they tend to form ionic bonds. So they're willing to give up their electrons to anyone who's willing to accept them. So I kind of like to think of them as the tramps of the chemical world. They're willing to give away everything they have. Now if we move over to the far right column, this family is the noble gases, and the noble gases, you'll recall, have a filled shell or an octet of electrons, and they don't really need anything from anyone. They're already happy, they've got their filled shell, and they don't need to associate with anybody. So I kind of think of the noble gases as the snobs of the chemical world. So now we come to our second row elements in the upper right portion of the periodic table, and here's where things get a little bit interesting. These, well, until you get to the halogens, these are intermediate in terms of electronegativity and tend to form covalent bonds, and this is what we're going to be looking at now. So here we have 4 elements going across the periodic table, starting with carbon, moving on to nitrogen, oxygen, and fluorine. Boron is a little bit different, so we're going to talk about that last. But then if we look at the electronic configuration of the valence shell, or I guess I should say look at the number of electrons that each of them has in their valence shell, this is going to dictate the number of bonds that they can form. So for instance, carbon, 4 electrons in its valence shell. It can share 4 electrons. It can accept 4 electrons in order to make 4 covalent bonds in order to obtain that desirable octet of electrons. If we move over to nitrogen, now nitrogen has 5 electrons in its valence shell. It can accept 3 electrons to make an octet. So nitrogen can form 3 bonds. Oxygen now has 6 electrons. We're moving over 1 family at a time. 6 electrons. In order to obtain an octet, it needs 2 more electrons, which have to be donated from another atom. So oxygen can form 2 covalent bonds. Now fluorine, like the rest of the halogens, has 7 electrons in its valence shell. It only needs 1 electron to complete its octet, so fluorine can make 1 bond. So here's a summary of what we've just mentioned. Now, for carbon, you can see we can make 4 bonds, and carbon is not going to have any lone pairs of electrons. Now, nitrogen is a little bit different. Nitrogen can only make 3 bonds. Right? So now we're showing 3 bonding pairs of electrons, and then nitrogen is going to have 1 lone pair of electrons. Oxygen can make 2 bonds, so we will have 2 bonding pairs of electrons and 2 lone pairs of electrons. Fluorine, as we mentioned, can accept 1 electron, can share 1 to make 1 covalent bond, and that leaves it with 3 lone pairs of electrons. Now let's look at boron. I said boron was a little bit different. Looking at the periodic table, we can see that boron has 3 electrons in its valence shell. So boron can share those 3 electrons to make 3 bonds. Right? So we add in 3 electrons from some other atom or atoms, and we've made 3 bonds, but boron still does not have an octet of electrons. So while boron is neutral, it only has 3 bonds. It has no lone pairs, no octet. Boron is electron deficient. Now, we'll see a little bit later on that boron could make a special kind of covalent bond by accepting a pair of electrons from another atom. So the other atom would have to bring both electrons to that covalent bond. That's a special kind of covalent bond that we call a coordinate covalent bond. So boron would like to have a relationship with somebody to complete its octet. However, if it does, whatever atom it forms a bond with is going to have to provide both of those electrons. All right. So if we look at our periodic table, we'll also notice that the elements that come directly underneath our row 2 elements here are going to have very similar bonding patterns. So our third row elements will have bonding patterns that are similar to the second row element immediately above it. So silicon will have bonding patterns that are similar to carbon. Phosphorus will be similar to nitrogen, sulfur similar to oxygen, and so on. But also remember that these third row elements have d orbitals that they can start to use. Remember that when we did Lewis dot structures, I told you that if you had extra electrons you didn't quite know what to do with, usually you're going to give those to the third row elements. Because the third row elements have those d orbitals, they can expand their valence shell and accept additional electrons. So while the third row elements will have bonding patterns similar to the second row element that's immediately above it, they will have additional bonding patterns. So this leads us to common bonding patterns for second row elements, and I'm calling these normal covalent bonding patterns. We'll talk about some other kinds of bonding patterns that you might see in some reaction intermediates, all right, where the atoms are actually charged, but these are for the neutral atoms, okay, neutral atoms when they form molecules, all right. So carbon, we said, could have 4 bonds. Now these 4 bonds could be 4 single bonds, as I'm showing first, or it could be a pair of bonds to the same atom over here, say some hypothetical element Q that it could be bound to. So we could have what we call a double bond and 2 single bonds. That's still 4 bonds. Or carbon could have 2 double bonds, so it could have a pair of bonds to one atom on this side, a pair of bonds to an atom on this side. Or those 4 bonds could be comprised of a triple bond and 1 single bond. So there are multiple ways that carbon can make 4 bonds. Again, 4 single, 1 double and 2 single, 2 double, a triple, and a single. Likewise, nitrogen can form 3 bonds, and those 3 bonds could be all single bonds. Remember that nitrogen is going to have that, always have that lone pair of electrons. Or I could make up my 3 bonds via a double bond and 1 single bond. Still have that lone pair. Or my 3 bonds could be made up from a triple bond. All right? So 3 bonds and 1 lone pair. Oxygen, remember, we said could have 2 bonds, and those 2 bonds could be 2 single bonds, plus 2 lone pairs. Those 2 bonds could be a double bond, all right, to some hypothetical atom Q, let's say. And I still have my 2 lone pairs of electrons. Now the halogens, all of the halogens can only make 1 bond, right? So you're going to have 1 bond and 3 lone pairs. Now, it's important that you memorize these bonding patterns, all right, because this is going to really help you a little bit later on when we talk about different ways to represent structure. And in many of these representations of structure, in particular the condensed representation and the skeletal representation, we don't show every bond and we don't necessarily show every atom. So you have to understand these bonding patterns in order to be able to interpret those representations of structure.